thank you for being so brave to join this presentation. The topic is pretty technical and you're probably not going to use this information ever in your life. So, just to make things clear. So I'm Carlo Bottiglieri and this is my colleague, Elena Vilchik. We both work in a company called SonarSource. The company is focused on writing code analyzers and code quality tools. We are specifically part of a team called the Rainbow team. We are using Rainbow Dash without permission, but it's our internal team, so it's not part of our marketing stuff. And our team, especially the two of us, is focused on developing the JavaScript analyzer and the TypeScript analyzer. TypeScript analyzer is younger for obvious reasons. Okay? So, yeah, let's show you what the analyzer does. So at least we are clear on what it means, an analyzer.
So I'll go with that part. Hello, everyone. So for demo, I have chosen the project which I really love. This is Prettier project. You probably heard of it. This is a tool which is supposed to reformat your JavaScript code. And I love it basically for two reasons. One reason, obviously, like this is a great tool. And another reason, like for some weird reasoning, they make really weird bugs, and this is nice for demoing it. So first thing is here we are calling a function, and in fact that function accepts only one parameter, and you are passing second one. Obviously nothing will explode or something like that. The last one will be just ignored by their function execution, and you basically have a dead code there, which is not bad at execution time, but bad for maintainers later on. You see these usage options here, and you think that, okay, that's options are there for a reason, but they're not. Another thing here, which is probably more critical, if you look carefully here, you see that this part over here and on the left are exactly the same. So you did probably some copy pasting or something like that.
You as in the Prettier developers.
Yeah, not you guys. You don't do like that, right? And so next thing, probably the similar thing. You did some copy paste. There is a case which is exactly the same as the one over here. So you have a pretty complicated for loop. So if the point was to really have the same behavior here and there, you probably better to refactor the code and move the cases to the same place. And or if it is a copy paste error, then of course you should fix it. Last thing in this project I wanted to show you is here we have isBlock, not isBlock being condition of ternary operator. So we have some true value, we have some false value. And in fact, this condition is always true here. Can you tell me why? Why is always true here? Yeah, because here in else if isBlock is true, we will return, and obviously we will not reach the next line, and we will reach it in only case when it is false. So there is no meaning in this empty string here. It will be just confusing. So that was it for this project.
develops, and it's open source just like the analyzers. So in general, we work on almost exclusively on open source, our team. We don't develop the UI, so the integration with the IDEs, with Visual Studio Code, Visual Studio, IntelliJ, Atom, etc. etc. It's not us because we are focused strictly on the analyzers themselves, and then the plugins are different. So in theory, all of the integrations can support all of the languages that even other teams, not just us, develop. Just to make you understand that we're not focused on a single language. We as a team, we are focused, but the ID integration is a bit more broad and generic.
And one more thing, if you have any questions, you are free to ask them during the presentation.
Yeah. So maybe we're going to have time at the end as well, but if you want to stop us at any moment, it's fine. So, in fact, before telling you how to develop an analyzer, exactly how it's built, there are things that we need to fix. We need to think about even before we get to the actual implementation of the analyzer. And this is especially true for JavaScript. It's a language that really forces us to think about a few things up front. So the first thing is that exactly which JavaScript you are targeting is not an easy thing to decide. First of all, it can be just difficult to say, okay, what's the version of JavaScript that I'm analyzing? Or am I trying to analyze any version of JavaScript? Or do we cover flow annotations? And do we support these specific file structure? Like, where is your JavaScript located? It's JavaScript files, but you also find JavaScript stuff in HTML files. And there is Vue that has the single file component thing that drops the JavaScript inside a specific structure. We've seen JavaScript appear almost everywhere, in XML, whenever you can. There was one guy once who asked if we could analyze JavaScript that was sitting as a blob into a database. So really everywhere. We do not do that. We have better things to do, but still. Just finding where the JavaScript is non-trivial. Then, on top of it, you get minification. So many times the JavaScript that you have in the project is not some JavaScript that you want to analyze. What happens if I start analyzing your bin or your webpack JavaScript that has been aggregated from all of your different JavaScript files, and since you dropped it in a folder that you did not exclude from analysis, well, I start analyzing it, and it's huge. It takes time for the analyzer to do that, and it generates maybe 100 or 1,000 problems that you don't care about because that's not your real source files. Because the particularity of JavaScript is that it's the source and also, let's say, the compiled version of it, because you're using plenty of tools that process the JavaScript to create an artificial version of JavaScript. Here, the classic example is minification. You use a minifier, and maybe you are not putting the minified files in a specific folder that you are not excluded from your configuration of the analyzer. So we end up having to find a way to ignore your minified files and not to analyze them. And this is just an example, but for instance, to do this, what we had to do was to kind of define the shape of the rectangle that is framing your code. Because typically minified code is much more broad than tall. So we said that if the rectangle looks broad, then it's probably minified code. It needs to be really broad, like 3-4 times your normal length of the line. Okay? And if instead your code looks more like a square or a vertical rectangle, then it's probably non-minified code, and then we need to analyze it. Just to say how crazy it is to have a good user experience in an analyzer in an environment where your code is both the source code and also the final, let's say, compiled code with dozens of different tools doing different things. Then there is also the problem of, okay, you want to write rules, code that is analyzing someone else's code. You need to parse that code. Which parser do you use? There are many good parsers, etc., but not all parsers give you a code representation that is useful for doing code analysis. many parsers give you a code representation that is good to do code transformations, for instance. But in order to really write rules, you need to have a lot of contextual information. So not every parser is providing you this contextual information. And here I give you an example. Take this function here. We want to implement a simple check that says that your list of parameters should not end with a comma. It's valid JavaScript. It works. But I take a very simple rule here. You don't want to find a comma. So what if your parser does not provide a good representation of the list of parameters? You end up writing something like this. So the only thing that you have is the element that says, give me the list of children of the root node. The root node being the function node. The list of children is the function name, parameter 1, parameter 2, and then the body of the function, in this case, equal me. So I want to iterate over P1, P2, and I want to have the commas, but I don't have a good representation of them. In fact, I discovered that they are lost into this big list of children which contain everything, the function name, the commas, etc. So what we have to do is, okay, let's scan through all of the children for something called function parameter, and look for the commas, count them, and if the number of commas is larger than the number of parameters, then raise the problem and say, hey, you have a trading comma. I'm not even trying to place the problem, to place the issue, but already this code is super complicated for such a stupid rule. What if instead the compiler is giving me a good structure that says, okay, this is the function, and the function has a property which is params? Well, I don't need to filter or anything, I just say, okay, let's take the last element of the parameters, and I do not assign last. It's let last equals function. Okay? So, and then I check that last is a comma. If the last parameter is a comma, I have the problem. So just this kind of forces you to consider the compilers very carefully. And let's imagine that you have picked it, the right one, and you are fine with it, and you start coding. Yep. So the other problem is that not a single JavaScript developer has the same idea of what is a good thing. Okay. Everybody has different opinions on the fact that, I don't know, not a number is a good thing, and that you should do monkey patching or not. No, monkey patching is a heresy. So the first thing that we decided was, let's make sure that our default profile,
it was working. Let's make sure that the default profile, the default rule set that we had, that we give you when you're using the analyzer the first time, is as uncontroversial as possible. So we are only raising stuff that almost everybody would agree with. So this is why we tend to focus the default profile, the default rule set, onto bug finding. Because everything that Elena showed you were things that were wrong. It was not a matter of use let instead of var or something like that. Okay? And then, even if you have very, very specific bug finding rules, even then, you cannot be sure that some cases where you think that there is a bug, that's going to be considered a problem by the developer. So what we do is that we use our overall code quality platform to collect metrics and to analyze dozens of projects that we typically gather from GitHub, etc., etc. That's how we get onto Prettier and say, Prettier is doing this and doing that, because we kind of scan multiple projects, and then when we develop a new rule, even if we think that it's technically correct, we go through some examples, some cases where this rule is raising a problem, and we check that this problem really makes sense. Beyond just technicality, makes sense for the developer. So, for instance, this one rule is about storing values that are not used. If you see, In the second usage of binary as base 64, we are assigning something, options.binary as base 64, which is not used again. So you're assigning a value, that value is never read. Okay? So obviously a mistake. We have no problem with this. For sure the developer did not want to do this. Okay? But the same rule in a different project, you see, this variable here is declared and we assign undefined to it. And then just after that, we assign this get status. There is no usage of that value undefined. There is no check. It's not if f is this, then do that. It's direct. So it's clearly useless. That assignment is completely useless. But then what we discovered that in the same project, so the same team has done this kind of mistake multiple times. This is another time. And it repeats. Wait, what does this mean? It means that even if it's technically wrong, it doesn't make sense, there must be some coding convention in the team that says that whatever happens, you always initialize your variables explicitly to undefined. We cannot expect adoption if we are bothering a team with something that they consider a best practice for them. So even if this is technically correct, typically we say, okay, if it's the first declaration, simple value like 0, null, undefined, we ignore them because people just use them to explicitly say, I'm initializing it with something. So we make sure that we don't raise this anymore. The only reason why this is still visible is that we had considered everything except undefined. So we have not yet implemented the exclusion for this rule, but it's coming, and this case is going to disappear. So we are sure that the only cases that will appear are the ones that are uncontroversial. This takes a lot of time, but it's worth it, because this way you reduce from 100 issues to 10, and all of them are really interesting, no matter which team we're talking about. Okay? Yeah.
Okay, here we were trying to think of a title, but didn't manage. So here we move into a more technical part, to really the inners of the analyzer, how the mechanics of it. And when we talk about average code analyzer, I think like most of them, we need to think about how compiler works, because these two tools they have partly the main part. So they work with code, and they need something at the end, and they need to parse this code in different layers to produce some information. So for compiler, for example, we do machine code generation, we do code optimization. That's all required for execution of code. But for code analyzer, we don't need code optimization. We don't need code as output of the process. We develop rules, of course, to raise this, to detect some patterns, to detect some bugs and code smells. And in order to make these rules smarter, we need some additional layers between. For example, here we have data flow analysis. We will talk later about it. What is it? So let's quickly go through some of these layers. Lexical analysis is the most simple one. You cannot do much based on it. Still you can. So what does it mean? You are taking your code, you just splitting it basically on the words. We call it tokens. So each this piece is a token. It has some kind. So you know that, okay, this token is keyword, this token is number, this token is punctuator, and already, in fact, based on that, you can have some rules. Just to show you, I will show you super trivial rule. Here we have a rule. Sorry, we have again one new way of showing issues. So this is an online REPL, basically. So you have, this is a rule about detecting usage of octal numbers. You probably know that if you prefix your number with 0, it will not be any more decimal number. It will be octal number, which might be misleading, and you might just write it to have like a right number of digits, something like that. But in fact, at the end, you end up with the wrong number. So in order to detect that issue, you don't need a syntax tree. And all you need is that, okay, here is my token. I know this is number. I know it starts with 0. Here we are. We have an issue. Next step is syntactic analysis. So this is what Carlo basically was talking when he was talking about, okay, which parser do I choose? Because the output of parser is the syntax tree. So syntax tree is just other way to represent your code in a structural way, to show the relationship between different words, different tokens in your code. So here, for example, okay, we have a function. Function has a name, has a parameters, has the body. In which case, this is a if statement. An if statement has a condition, which is a strict equal in this case, and the body, which is call expression. And if we go deeper, we have operands of the expression, which is in condition, and we have the call Kali and the parameters, arguments of Kali, of call expression. So all of that now is not just a sequential set of tokens, but it's now structured in a way that you see how they are united. And if you look at this, at the leaves of this syntax tree, you will in fact see the result of the previous layer, previous analysis, which is the lexical analysis. So you see tokens there. Of course, this syntax tree is super simplified. It's just to show you the idea. And in fact, you can even structure it a bit differently, as Carlo was speaking about. So you can either have everything like all children are all alike, or you might say, okay, these children are parameters, these children are function name, and so on and so forth. So this layer, this analysis, is like the most basic analysis you might have, and all of the analyzers are using it for 90% of their roles. And to demonstrate it a bit, I created this code sample here with the empty block and empty object literal. So if we take a step back on lexical layer, they are exactly the same. You have curly brace, curly brace. But here we really want to distinguish because we know that empty object is not empty block. And we don't want to raise an issue for empty block here. And here, that's where a syntax layer will help us, because he knows that, okay, in condition, you cannot have code block. And vice versa, in the place of the statement of if, you cannot have object literal. In fact, you can have.
Yeah. You can have an object literal, but we kind of default to think.
No. In fact, no. The parser forbids that.
Yeah.
If you want to have the statement which is just object literal, you have to put in parentheses.
Yeah. Yeah. So that's almost up to the point where the standard parsers bring you, and that's what you do to implement most style and basic rules. But if you want to implement something more interesting, then you need to start building more advanced code models, so that you can write your rules on top of a code model that is not just a representation of your simple code structure. And the first of these more advanced code models that typically we implement is what's called the control flow graph. Control flow graph is not representing the code structure. It's not showing you that an if contains something. It's representing the potential transitions, which different steps will be followed by an interpreter. So it's more about the execution. And this is very important for us because most analyzers, and ours is no exception, are static analyzers. You don't really execute the code. You don't run the code. You are not interpreting it and running results or anything, because frankly, that will mean that most code is impossible to execute outside of its normal context, like outside of the browser, etc., etc. So it's very important for us to create a representation of how the code would execute. For instance, if I were to ask you, what's the first expression that is going to be evaluated by an interpreter when this function gets called? Which expression in this piece of code is first interpreted? Sorry? There is nothing there. There is nothing to evaluate. So what else? Some interpreters might decide to go there, etc., but the reality is that typically not. So, come on, I'm going to be stuck here if you don't answer. Sorry?
I is undefined.
I is undefined.
No, let's say which thing will be computed first.
I is undefined is already a problem. So something has happened, it has raised an issue, etc., etc. But just trying to evaluate which expression. For instance, if I were undefined, where this would happen? Where would we find that I is undefined? At which moment? Sorry? Speak higher. I cannot. Exactly. So the first expression that gets really evaluated is the comparison of I with 10. So I smaller than 10. Okay? And then, next thing that happens, if this comparison returns true, then we evaluate the second part of the conditional structure. Okay? And then we enter the if block and we evaluate the invocation array.push. Okay? And then that's the point where there is the incrementer. And after that, what happens? We go back, and this is the loop. So your graph represents the loop in this way. You can navigate it. You can write code that says, okay, first block, the first block that gets executed is I smaller than 10. Next, p is strictly equal to true. Next, array push. Next, e++. Next, I'm back at the original point. So this is a loop, and you have identified what are the different steps of the loop. But this is not enough. This is not all of it. There is more. So if p equals true was false, we will move to the else part of the if statement, and then we will return, and the function will be over. But there is still one thing that is missing, one branch, one logical branch. Can you tell me which one it is?
False case of the
Indeed, the shortcut false, which bypasses the second entirely. And so this is your full control flow graph from a very, very simple function. Okay? And we need to build this. We need to write the code that takes just the abstract syntax tree and navigates it in such a way to create this kind of graph for any code, for any function. And the funny part is how to build this. It's extremely difficult to unit test the fact that your graph looks in the right way. It's difficult to write a unit test and say, okay, now I want to have this block and then this other block and then this other block, and then I write the implementation of the control flow builder in the way that this matches. So the first thing that we implement is this tool. When we have to implement a control flow graph, the first thing that we do is implementing this software which we call the CFG, a control flow graph viewer. It's something that is able to execute the control flow graph builder and then represent it graphically. So the idea is that we develop, and then every time we add a little bit to the builder, we see if the graph looks in the way it should. So in your mind, you imagine, you do the exercise that you just did, asking your questions. So what is next, what is next, what is next? And when the graph visually looks like what it should be, then you are probably done. You take this representation, we ask the viewer to generate a JSON representation of this, and we put it in a unit test. So the JSON can be very rich, very complex, but once it's in there, we have a kind of non-regression test that guarantees that this kind of code structure always maps to this set of control flow blocks. Okay? So let's try, for instance, this is the implementation of the control flow graph builder. This is all the code that is going through the EST and building the control flow graph. Let's imagine that we are implementing the if statement and we've made a mistake. We have put the wrong. By the way, maybe this will also give us an interesting result. Let's see. No. Refresh. Not sure. I did not prepare it. No, indeed, this is just completely broken.
You just didn't refresh.
I didn't refresh? Oh, no, I didn't refresh.
This is my computer, so...
Yeah. So it's not entire. No, it can zoom like this in this crazy way. So you see, I'm not getting the right control flow graph. Both the true and the false branches are pointing to the same block. So it's very obvious visually, if we have a good image in your mind of what it should look like, that this is mistaken. Okay? And let's make yet another change. Let's say that we inverted them entirely. Click. And refresh. It's an internal development tool. It's not the most polished software in the world. And of course, at times you make mistakes while writing the CFG viewer. So you make mistakes with the viewer itself, and it's yet another problem. So here, if you're careful, you notice that the true branch is pointing to the false statement, and the false branch is pointing to the true statement. So you can spot all of the small mistakes, and when you're fine with it, transform into JSON and place it in a unit test. Okay. It takes weeks to write the full builder for a language as rich as JavaScript for any case. Switches, continuous breaks, etc., etc. It's really a pain, but also funny. So on top of this code representation, we cannot write so many rules. It's powerful, but when you start thinking about it, there are not so many interesting problems that you can spot with just this. If you add an algorithm that is called live variable analysis, you can implement the rule that I've shown you before, that was finding when values were unused. So you couple the control flow graph with the live variable analysis algorithm, and then you can start spotting unused values inside variables. But beyond that, you are kind of, we'll say, stuck. You can do a few things, maybe finding that code you can find, but not much more. But what if we do something more on top of it?
And that's where, in fact, interesting part starts, finally. So data flow analysis, that's how we call it, not only us. So you can also hear it maybe as symbolic execution. So you take this CFG control flow graph, which we just built. So you have this path of execution in your program. And on top of that, you put the layer of data. So you're trying to keep the track of all the information you can infer from the execution, and trying to, based on this information, detect some bad patterns. So what does it mean? What are you doing?
You don't want to demo it?
No.
No, okay.
We are super team.
Yes, indeed.
So let's understand what does it mean. So I put the questions marked between the lines, like first and second line of the function. What can we say at this point about variables? I mean their values. It's not could be. Okay. You are going too far. I'm talking about that particular line. So because we are really going through control flow graph. So we are at that particular point between these two statements, and we don't know what will be there. If we could, okay, that's too smart. But we are in that point, And we know only that we are 100% sure that message is undefined at that point, right? Because when you create variable, it's not initialized, it has undefined value. So, and then the data flow analysis is basically we creating these program states for each point of your program, for each execution flow. So let's try to do that. So if we go inside of the if, we create, we still have message undefined. There are these small errors to show that we are before assignment. So we still have message undefined, but we add in one more information we know, which is p equal true, which is because if we are inside of that condition should be true. And when we exit, I'm continuing the same the same execution flow. We are just before the statement. We have the message with the string print me big. We have p still equal true. And when we execute the last statement, it's all nice. We are printing print me big. And then the most interesting part starts exactly when we are not entering this if clause. So we are going straight to this point. We are not entering here, as control flow graph will point us. And we're going exactly here with the value undefined because we didn't execute assignment. And of course we will get the type error at the point, at the last point.
An interesting detail is that not only we know that message is undefined, which is relevant for this problem specifically, but you see, we also know that P is different than true. So we collect everything because you never know in advance what's going to be a problem. Not just what is undefined, but also what you have learned from other conditions. Now we demo.
Let me show you some examples to show you more this analysis, this kind of analysis. So let's look at the first function. Here we have, so this is super easy. We have a condition which is x equal undefined. We will get the type error when we will try to access the property here. And in fact, I created another variable which is the same value. And here we know that even if x is undefined, a is also undefined because they are they're referencing the same value. And the point is that this knowledge of constraint on the variable, that's how we call this knowledge, that x is undefined, has the strength only here, only in the block, which of course makes sense. And it does in fact opposite strength in the opposite. And it has no strength in outside of the condition. Then another example on how we can apply one knowledge on the top of another knowledge. For example, here I'm first checking that x is not truthy, let's say, and then I'm checking that the type of the x is string. Then you should probably know that the only string value which is not true is empty string, and then we are getting this we're getting this condition which is always true. And the last but not least is around the relations between variables. So here created the variable which keeps these two relations connected with the OR, a greater than b or b equal c. Then we enter the condition. That means that this all is true. And then we checking if A greater than B, so we return 0, else, and then we go to that else, we know that, okay, condition was true. That would mean that either this true, either this true or this true. As this we already considered, then this is not true anymore. We cut it away. And the only thing which is possible is that B greater than C. But here we're checking opposite condition. And of course, we're sure this will be always false, and there is a dead code over there. And if we go deeper into data flow analysis and we consider the problems which we face, this is in fact when you have a cross-procedure, cross-function execution. So you have, so in this example, I just refactored a bit the example from previous slide, so that you have exactly the same thing happening, but this access to the message happening not in the function itself where you don't assign the value, but in the some nested some other function. So at the point when you arrive here with the program state message equal undefined, you cannot say anything because, okay, it's not criminal to pass undefined as argument. But you can go deeper and pass this program state, transform it so that you match the arguments of parameters, and you say, okay, text is undefined in this case. And in that case, you can always also raise an issue here the same way we did it previously. So that's in fact what we are currently working on. From the first side, it looks like straightforward. Okay, you have function, just enter it and do the same. But it's not trivial from performance point of view, and that's where we need to work on.
Well, there was just a talk about performances in this same room. So, can you guess why there is a performance problem there? Exactly. Indeed, there is a combinatorial explosion. So we need to introduce strategies to minimize it, like checking if two paths bring us to the same point in the program with the same state, so with the same set of constraints known, exactly the same. In that case, we kind of merge the two paths and only proceed with one of them in order to reduce the number of combinations.
And another thing in that in JavaScript, you call some function, you don't always know where is this function, where is the implementation of this function. And that's also not trivial.
And if it's a function expression associated to a variable, well, exactly which declaration of that function is being used at that moment in time. So it's not always just a function declaration that is kind of stable.
So that's basically the state of art in our analyzer, and that's what we plan to work on next
few months.
Next few months, yeah.
So there is all of this, but then as the code analyzer needs to do a bit more, especially if you want it to be used in large projects that have a history, that need to have an overall view of how the project is going from, let's say, an overall quality point of view. So
Sorry.
Where are you going? We are so great in coordination today. And so the analyzer, our analyzer typically needs to push to our overall code quality platform. You don't have to use it, of course. You can use the analyzer in the IDE, but if you also want to have all the full history, well, the same analyzer is pushing information to SonarQube, which is the long-term project quality platform for your given project. Again, open source and free and whatever. And this way you can see the history of your metrics. You can see for instance, let's pick one, number of lines, it's yeah, lines of code is more interesting. And you will not guess how difficult it is to find the actual executable lines in a JavaScript program, really counting just the lines that get executed, not the comments and not the closed curly braces on their own line, which don't count as executable code, etc. It's pretty difficult. And you have other metrics like code duplication. So the analyzer needs to do this code duplication chunks collection, so it collects all of the potentially duplicated pieces of code, so that then it can be pushed to the platform, and then the platform can show you the overall percentage of code duplications for your project or across multiple projects. If you are using the same code quality platforms, you are using the same instance of SonarCube for like 20 projects. Every time you analyze every single project, the different analyzers will push the duplicated code chunks, and so it will be able to say, okay, you have code duplication between these two different projects. And this is, of course, part of the analyzer as well. And it's not just a rule. It's not something that you apply on a single file. Okay? And then, of course, you can have tracking of the status of your code smells, of your vulnerabilities, bugs, etc. And then one important thing, typically in big projects, where you have a long history, is this concept what we call the leak period. So typically, I'm sure that almost all of you have seen this, you start trying to evaluate the quality of your project and you find that it's crap. Right? Not because you are bad, of course, but because management pushed you to go too fast, etc. It's never the fault of the developer. But the developer needs to fix the problem. And again, I'm sure that you have seen this happening very frequently. When you find out that your code is crap, well, fortunately, this example is not so good. In fact, this is the code analysis of our analyzer. So this is SonarJS source code is being analyzed by the analyzer. But let's imagine that you don't have like big effort. So this is instead the analysis of the platform, of what you're seeing. So we have 10 bugs in there. We could have done better. Typically, in a newly analyzed project, you find like 2,000-3,000 code issues. If you look at the projects that we were analyzing for finding, let's say, interesting new issues for our analyzer, those projects frequently have thousands of problems. And of course, every manager of software development in the world will come and tell you, now we stop all developments, we stop delivering anything until we bring that number to 0. Happens all the time. Okay. So for those cases where it does not happen, rare, the idea is we don't just tell you you're in a bad situation. You can set up a period, let's say the last 3 weeks of development, the last 2 weeks, the last month of development. You have been coding on this project in the last month. It's, let's say, in the preparation of the new release. So we only show you the new things, the new bugs that you have introduced. Again, we could pick a better example because there are no new bugs in the future.
There are code smells.
There are code smells. Yeah, they're not taking care. It's not the same team, so we are free to. I don't know what they are doing, those guys, but they have introduced 2,600 code smells over the full lifetime of the project, and 69 new code smells in the last iteration. Code smells are not bugs, of course, it's just suspicious stuff, like, are you sure you want to do that, etc., etc. So the idea is that this way, you know what's your direction. It's the first derivative of your code quality. It's not the overall situation, it's the tendency. So this way you can say, hey guys, we're not going to fix the 2,500 code smells, but let's make sure that in this release, in the next release that is coming, before we release, we bring this down to, I don't know, only 1-2 new code smells. Okay? This way, this is kind of defendable. You can go to management and say, guys, we just need a couple days to bring this under control so that the overall quality doesn't get worse. And in fact, if you keep on doing this, for every release, well, the overall code quality starts to get better. Because if the number stays stable, but the amount of features and the amount of lines of code increases, it means that on average, the code quality that you have is getting better and better, and it's much more defendable. Okay? So this is, for big projects, quite important. So once you get there, I would say you have most of what it takes for small, medium, large projects with small, medium, large teams. Okay? And that's about it. There is not much more. So thanks a lot. And if you have any questions, fire away. No questions? Really? Yeah, someone.
What languages are you writing your analyzer?
We, as me and Elena, JavaScript, TypeScript.
No. Which language we use?
Oh, that's a very, very interesting question.
Thanks for asking.
Thank you. It's a great question. So the JavaScript analyzer is written in Java. Yeah, don't kill us. It's 37,000 lines of code. Of course, if we had written it in JavaScript, it would be only 5,000 lines of code, but it wouldn't work. So we kind of draw a balance. But that's fine for us because you remember when I was explaining the thing about the parsers. JavaScript is such an open environment that we cannot just say, okay, let's use this parser from the Babylon parser, and it's going to be fine. So what we have to do is to write the parser ourselves. And if you have to write a parser, and you're also working on other languages, maybe not just us, but another team, we have a framework for writing parsers. So we gain some time. But instead, for TypeScript, we took a different decision. For TypeScript, we wrote the analyzer. The SonarJS analyzer is written in TypeScript. Why this? Because TypeScript is much more structured environment. You have one mainstream parser for it, which is the Microsoft TypeScript parser. It's open source, so we don't have problems with licensing because, again, we need to stay open source ourselves. And it's pretty well documented, which is another problem with parsers. At times people just write a parser, but it's not documented enough for us to exploit for real. And it is not just built as a parser, it's built as a parsing front end. It gives you a lot of information. You remember the idea of having a separate list of parameters instead of a generic list of children of a node, etc. We have we have looked into the TypeScript parser for Microsoft and we said, okay, it's so structured and it's clearly targeted to building tools on top of it. It's not a closed parser. You look at the Swift parser, it doesn't look the same. It's clearly something that is built to be performant, robust, whatever you like, but it's not built to build tools on top of it. So if we were to take it, we'll be in a kind of difficult situation. Try to build a symbolic execution, a data flow analysis engine, and you discover that the underlying parser 2 levels below is not giving you, I don't know, if there is a semicolon or not. You're just stuck. While the TypeScript parser was different, so we say, hey, let's take the opportunity, we write it in TypeScript. Now, yes. I can repeat it because I should have a microphone that works. I should.
It works?
I don't know.
Yes.
Repeat it yours.
What is the rate of false positives of our products?
Yeah.
I don't know. should be around 0. You know?
No, giving a number is difficult.
In fact, if you would ask this question this spring, the answer would be like a lot. Especially, let's say, not false positives, but we call them deal breakers. like this the undefined assignment as we showed. So from developer point of view, this is a false positive. From our point of view, this is not. You're assigning a value, it's not used. So already here, it's not clear how to answer. And we did a big effort to sweep away all of that deal breakers. And I would say that on the main profile, the default profile which we have, you should have really not many false positive.
Yeah.
Because that's really our target. That's what we're trying to make.
And is it customizable?
What exactly?
The set of rules you mentioned.
Yeah. So you can customize it with here with interface. So for example, for JavaScript, we have one profile which is default, which has just 66 rules. Then we have another one which is we call it recommended, which is wider. And of course, you can create your own. Like here, we have our own. You can activate, deactivate.
If I want to have some really custom, not existing rule,
It's possible for JavaScript, yeah.
via plugins,
Yeah.
and I can render it by myself.
Yeah.
Yes, but you
Java.
need to code in Java. But for SonarJS, since it's written in TypeScript, you can write your own rules in TypeScript. Maybe another point. Let's say the amount of false. Elena kind of hinted at it, but if you really want very few false positives, it's better if you stay with the rules that are part of the default profile or the recommended profile, because most of the effort to reduce the false positives is in the rules that belong to those profiles. The rules that don't belong to those profiles are styling rules, or really open-ended bug finding or code smells. So there we don't focus so much on reducing the false positives, because the idea is you have activated the rule. You want that rule. So you're going to be a bit more tolerant of false positives because you wanted it. You wanted that specific rule. While for the default profiles, we're really radical on it because it's not a choice. It's the default behavior.
You mentioned several projects which you already have analyzed, and you mentioned performance problems. So what is the average time of analyzing one project? There are 20 projects and they have different sizes, but
In the minutes most of the time.
It's less.
Yes, for a big project.
The analysis of itself without sending the results to the platform, I don't know, 10 seconds, 20 seconds.
No.
No.
No, if the project is really big, you might have the minutes.
So we have on our test environment we have around 7,000 files, and we're analyzing them like in 3 minutes, something like that.
Yeah, and if you're using it just in the IDE, well, it's only analyzing the files that you are touching or the files that you are changing lately, etc., etc. So it's built to be in the milliseconds in that case. But of course, there are crazy people that are running the analysis of the Linux kernel using the.
It takes hours, yeah.
That takes hours, and it's not in JavaScript; it's in C. And if it were JavaScript, it would take probably weeks.
So thank you.
Thank you.